This is the 5th video on electromagnetism for A-level physics. The aim of this video is to go through a few calculation type questions relating to Faraday's law. Before we get into the questions, we should just write down Faraday's law again for reference. So Faraday's law, as we saw in the last video, states that the induced EMF, that's the voltage we create, is directly proportional to the rate of change of flux linkage. Remember, flux linkage is another concept that we saw last video, and it's n phi, where n is the number of turns in a coil. We can promote this proportionality up to an equation that will actually allow us to go through some calculations, and that's what we're really going to be using in this video. EMF is equal to the rate of change of flux linkage, so change of flux linkage over time. This can be rewritten, it might seem a bit easier to use this. Number of turns times by, or loops, multiplied by the change in flux and divided by the time it takes for that flux to change. Okay, so the first one, so example 1, let's consider the following. A rectangular loop measuring 40 by 60 centimeters is located entirely within a uniform magnetic field of strength 200 millitesla. The loop is at the right edge of the field, and then the loop is moved to the right at a constant speed, and it leaves the field completely in 3.5 seconds. So we'll draw out a picture of this to get to grips with what's going on. So we'll need a magnetic field. We'll say that in this dashed region here, the field is directed into the page. Right, again, that's what that symbol means, into the page. We'll draw in our loop. So the loop is located at the edge, like that. And this loop, being in this field to start with, has some amount of flux passing through it. We can represent that with a few field lines. We don't need to draw the whole field. A short time later, the loop will have come out of the field. So we'll draw the loop later. It's come out of the field. So that's the loop 3.5 seconds later. To start with, there used to be field lines going through this loop, right? In the pink case here, there is some flux, because we can see that because there are some field lines going through it. But here, this has left the field, and the consequence of that is that there are no field lines going through it. There is no flux, so the flux has gone to 0. Let's add the dimensions mentioned in the question. So 0.6 meters is the width, and 0.4 meters is the height of this. We can deal with some calculations. We saw that the field strength, right there, is 200 milliteslas. So B, magnetic field strength, is 200 times 10 to the minus 3. Remember previously that flux is calculated as VA. So we've got 200 times 10 to the minus 3 multiplied by the area of the loop, 0.6 by 0.4. Area, field strength, and field strength. So we can get that. And now, as the number of turns aren't stated, we always just assume there's only one turn in a coil if the number of turns is not stated. So it's just a single loop. It's not really a coil. We'll say n is 1. We can calculate the value of phi, the amount of flux. The flux is 0.048. The units for flux are Webers, WB. So we've got the amount of flux. Now, we know that this has got something to do with Faraday's law at a glance, or even something to do with induction, because the flux changes, and we've said repeatedly throughout this series, if the flux or the amount of field through a loop changes, then there must be an induced EMF. We've shown that. But Faraday's law is a bit more specific. Faraday's law tells us that the induced EMF is directly proportional to the rate of change of flux linkage. We've got this equation here, or this one here. So we can actually calculate that quantity, EMF, if we just multiply the number of turns by the change in flux and divide it by the time all of this took. Well, the number of turns is 1. The change in flux, slightly overkill the way I'm going to do this now, but that would be the final flux minus the initial flux. The final is 0, it's left the field. The initial was this value that we calculated up there, 0.048. So we get minus 0.048 as the change in flux. We're not really interested in the sign, so we'll just say that it's positive 0.048. We just want to know the amount by which it changes. And then applying the equation of Faraday's law, we've got 1 times by 0.048. If we look back at the question, we were told that this takes 3.5 seconds. So we can divide this by time, divide by 3.5, and we can calculate that value. And that comes out to be 0.0137. It would be more appropriate to state that in millivolts, 13.7 millivolts. Not a big voltage. We're not going to solve global energy needs by waving this loop back and forth here between the blue and the green, the blue and the pink position here. But it is still something. We could scale this up and go somewhere with it. But that's the answer to that question. Right, we'll go on to consider example 2. A rectangular loop measuring 20 centimeters by 40 centimeters is placed at the edge of a uniform magnetic field. The 40 centimeter length is parallel to the edge of the field, and the loop is moved out of the field at a rate of 5.2 meters per second. The field strength is 0.42 Tesla. First part of this question is calculate the EMF induced and the time for which it is induced. We have a picture. So we've got the field, which is taking up this, occupying this dashed region here. We're showing that the field is into the page. It's a uniform field. We're told in the problem that the 40 centimeter length is parallel to the edge of the field, just like it is here on the right side. And so the height of this shape should be 0.4 meters and the width should be 0.2 meters. We know from the last question that we can use this equation. So EMF is equal to the number of turns multiplied by the rate of change of flux. There's just one turn, it wasn't stated, so we'll just say it's just a loop, it's not a coil. The amount of time this takes, well, if this were to go faster, it would take less time. If the loop were to travel slowly out to the right, then it would take a long time. So we should think to use the speed to determine the amount of time this takes. If something travels at a constant speed, speed is distance over time. Well, here we should think about the journey this has got to go through. For this to leave the field, it's got to get itself into this position. So the leading edge here, the one that I put a little bit of blue on, and then a bit more blue there, has got to travel 20 centimeters. In fact, the whole loop moves 20 centimeters. We know the speed is 5.2 meters per second. We know that it's got to cover a distance of 20 centimeters, 0.2 meters. And then we don't know the time this takes. So we can rearrange that equation. say that time is equal to 0.2 divided by 5.2, and that is 0.0385 seconds. Before we can go ahead and set up this equation, we need to know one other thing. We need to know the change in flux. So that's going to be the final minus the initial flux. Well, the final flux, that's in the blue case here, it's outside the field. There are no field lines passing through this, so the flux is 0. And the initial will be B times A. B, we were told, 0.42 Tesla, 0.42. And then the area of this shape, well, as it's a rectangle, the area of the shape is just the two side lengths multiplied together, the width and the height. So we've got 0.2 by 0.4. So we can work this out. Slight mistake, that's negative. And the value is 0.0336. We've got the minus sign there, but we don't really need that. We're not interested in directions here. We're just trying to establish how much the flux changed by, not by whether it really increased or decreased. That doesn't matter to us. Now we can assemble this equation here, circled in blue and white. So that is the equation from Faraday's law. So we know that there's one term, so 1 times by the change in flux, 0.0336, and then we know that this takes 0.0385 seconds to take place, and that will give us the EMF, which is 0.873 volts. That's the EMF, or the induced voltage there. Okay, we'll take this question on a bit further. So the loop is going to be repositioned, and I'll draw a picture to show what that looks like. So in the picture here we can see just how the loop has been repositioned. It's still inside a field of the same strength, it's just been moved within the same field, so we can still say the field strength is 0.42 Tesla. It's the same loop, so it's got the same dimensions, 0.2 by 0.4. But it's now been pushed back. It's 0.3 meters within the field. So if it wanted to get, if it were to be moved out of the field, it would have to be moved through 30 centimeters to do that. Again, the loop is moved at 5.2 meters per second. We've got that arrow showing that it's going to go to the right. And then we'll look at question C, which relates to this. Sketch a graph of voltage against time for the loop. The time axis runs from 0 to 200 milliseconds. We'll sketch out some axes to work with. Say that's 200. The horizontal axis is time in milliseconds. The vertical axis is voltage, or induced EMF, and that's in volts. So let's break this down. When the loop first moves, it moves 30 centimeters to the right as it approaches the right edge of the field, right, that white dashed line on the right. During that time, it has the same amount of flux going through it. I'm drawing some field lines to show this. It's in the same field with the same strength, and it's got the same area. So its VA doesn't change, its flux doesn't change. So for the first 0.3 meters of travel, the flux is 0. So in terms of distance from 0 to 0.3 meters, the flux, specifically the change in flux is 0. It stays the same. So we need to relate this to a time. So we'll take the distance it covers, 0.3 meters, and divide that by the speed at which it travels. That will tell us the time that it takes to cover that distance, which is 0.057 milliseconds, which is 57 milliseconds. So on our rough scale here, which is really just a sketch, we put in 100, 50, and 150 milliseconds. So up until some point, just after 50 milliseconds, absolutely nothing happens. So say that's 57 there. We can see this if we look at Faraday's law. EMF is equal to N times by the rate of change of flux. Well, this is one term, it's just a loop, and then the flux doesn't change at all. It's over 57 milliseconds. Well, 0 divided by anything is still 0. So that's why we saw no voltage induced. In the next stage, it's going to work its way out. So the loop's going to find itself in this position, just on the other side of that white dashed line. And here the flux is going to change. It's going from being in the field, having field lines go through it, to not being in the field and having no field lines go through it. So we should work out the change in flux that takes place in that stage. So it's already travelled 0.3 meters, and it's going to travel another 0.2. Its width is 20 centimeters. And in that stage we want to know the change in flux. So we have the final minus the initial. Well, the final is 0, ends up outside the field, with no field lines passing through it. The initial, we'll just use BA. Right? If we want to work out flux, we use BA. So that's minus 0.42 multiplied by the area of the loop, 0.2 by 0.4. Well, that's what we had in part A. It's exactly the same sort of thing. We actually worked that out right there. 0.873 volts. So we'll say the top of our scale is 1 volt, so that would be 0.5 volts, and somewhere around here that would be 0.8, so 0.87 would be about there. So we can put that into the graph. So all of a sudden it leaps up as we start changing the flux, and for some amount of time that voltage is going to be induced. In part A, we did work out the time that this took. We saw that it takes 0.0385 seconds, or 38.5 milliseconds. So we need to run from 57 up to 95.5. So we can see I've slightly overshot with this. If we come back a bit, 95.5 is probably about there. Just draw this in. So during that stage we get a voltage of 0.87 volts from 57 to about 95 milliseconds. After that, let's look at the next stage, because we're running this problem all the way up to 200 milliseconds, and it's still got about another 100 milliseconds after 95 to keep travelling. So it carries on going forwards like that. Well, the flux here at this stage where it's green is 0, there's no field going through it, and again later there's still no field going through it. If we go from 0 to 0, there's no change in flux. So from 95.5 milliseconds to 200 milliseconds, the flux goes from 0 to a flux of 0. There's no change in flux. So if we look at Faraday's law, N times change in flux over time, N times 0 over time, 0. It doesn't matter what N or T are, as long as T is some finite value. We get an EMF of 0, a voltage of 0. So for the rest of this, it's not really very useful. It doesn't induce any voltage, and that's what that graph would look like. Okay, we've got just one more part for this, part D. Okay, so in part D there's just a small change. Basically, if the loop is rotated 90 degrees so that the length is now the width, so the 40 centimeter length is now the width, how would the voltage against time graph differ? Let's just draw this out, see what's going on. So we've got our region magnetic field, standard uniform field directed into the page. And then we've now got our loop arranged like this, where the width is 40 centimeters, 0.4 meters. It still sits at 0.3 meters away from the edge, and the height is 0.2 meters. The loop still moves at the same speed, so it's going to take the same amount of time to cover that 0.3 meter distance. It's still going to take, as we calculated up here, it's still going to take 57 milliseconds to do that. And if we draw the loop later, in that case, like this, sitting in that position, it's gone from phi being equal to the full amount, right, BA. It's gone to that, and it was that to start with. We had the full flux before, the full flux after, no change. Delta phi is 0. And as we've seen, if delta phi is 0, EMF is 0. So the first bit of the graph is exactly the same. That's unchanged. The next bit is where we see some change. Previously, when this was arranged portrait, when the loop was arranged portrait, it only had to travel 20 centimeters to get out of the loop. So it didn't have to go that far, so it got out very quickly, changed its flux quickly, and induced a sizable EMF. In the next stage, the EMF was 0.873. But now instead of travelling 20 centimeters, it's got to travel 40 centimeters to get out. It's got to get itself into that position. By going from here to here, that's 0.4 meters of travel, twice as much as before. So we would expect the voltage to be half the value, but let's just check that. Let's actually calculate that. So the time, which we need for Faraday's law, is the distance, 0.4, divided by the speed at which we cover that distance. That is a time of 0.0769 seconds. And then applying the equation for Faraday's law, we've got EMF equals N times by change in phi over T. The flux change is the same as we saw before, so that flux change is, we saw that way back, 0.0336. It's still the loop losing all of its flux, but it's over a different time now, 0.0769, and this should be multiplied by 1 because n is 1. And then we'll calculate that. But we had thought already that this would be half of 0.873, and we get 0.437, which is half of that value, half of this. So the graph would change, and we would get half the voltage induced. So it would go up to 0.437 instead of 0.87, and that would travel across like that. But because it's got to go twice the distance, it's going to last for twice as long. So instead of just being that 38.5 millisecond run of voltage, it's going to be twice that. So we're going to end up with 77 milliseconds. So going from 57 to 77, that will take us up to 134 milliseconds. So this is in the second case. Also the second case follows that bit as well there, and under the orange is on 0 as well. Then after that, the loop has left the region where there is magnetic field. So when we go from here to here, there's no change. We've got, again, a flux of 0 going to a flux of 0. So taking those two together, the change in flux is 0. But we know if the flux doesn't change, we can't induce any EMF. So we're back to what we were getting before, just that it happens later on in the process. No EMF is induced. that's how that graph looks different. It's basically been stretched by a scale factor of 2 because everything took twice as long, but all of the same things happened. Okay, that's the end of that question. In the next video, we'll see a more challenging optional question. Okay.